Hello and welcome to the Chemistry Thanksgiving video. Hope that you have a happy Thanksgiving, and this is the Thanksgiving booklet to keep you fresh and to keep you ready for the ACP at the end of the semester, okay? So this is going to be a review of everything that we've learned since the first day of school until right about now. So as you're watching this video, fill out your packet, and there's going to be times where you have to press the pause button in order to do that. The first thing that we learned about was physical and chemical properties and changes. What is a physical property? Physical properties are traits about matter that does not change its identity. So that's one of the things you want to think about when you're trying to remember physical properties, okay? You're describing matter in a way that doesn't change its identity. What are chemical properties? Traits about matter that describes ways that it can change its identity. So make sure that you write the definition of both a physical and chemical property in your booklet. Now let's talk about some examples of both physical and chemical properties. Let's look at physical properties. Color, shape, size, density, amount, and volume. Malleability, that's the ability to hammer into sheets. Ductility, the ability to stretch into a wire. Boiling point, melting point, and conductivity. Is heat or electricity able to pass through the substance very easily? All of these are physical properties. Next, chemical properties. Flammability, so the ability to burst into flames. Anything that has to do with rust. Oxidation state, so negative or positive charge of an atom. Burning, combustibility, the ability to combine with oxygen in order to react. Corrosion, okay, anything that's eating away at something. And reactivity, okay? So make sure in those two boxes on your booklet you write down physical properties and chemical properties. While you're doing that, some of the key words for chemical properties, remember, chemical properties has to do, you're describing matter in a way that talks about how it can change. So anything that talks about reactivity, anything that talks about flammability, combustibility, okay? You need to remember these key words, okay? Let's move on to physical and chemical changes. So let's define both, okay? What is a physical change? A physical change is a change in which no new substance is formed. On the other hand, a chemical change is a change in which a new substance is formed, okay? So there is a change, but either the substance is still the same substance or we have a totally new substance, okay? So here are some examples of physical changes, okay? So on your little box in your booklet, please write these down. And I'll let you look at these examples, okay? Write them all down, but some of the biggest ones are cutting hair. If you cut your hair, the hair that falls on the floor, yes, it's shorter, but the hair on the floor is still the same hair as your hair on your head, okay? Anytime you chop wood, you shred a paper, you fold a paper. Breaking an egg, breaking glass, okay? Changes happen, but it's still the same substance, okay? Pay attention to melting ice. Pay attention to boiling water. Also freezing water. This is a physical change. Anytime you're changing between states and matter, solid, liquid, and gas, it is a physical change. Do not get confused. Because even though water has melted from a solid to a liquid, it's still water, okay? A lot of people get confused and say, well, it chemically changed from a solid ice cube to liquid water. So it's chemical, but that's not the case. It's a physical change. It's changed its form, but it hasn't changed its identity. It's still H2O throughout, okay? Let's talk about, I just talked about this. Anytime you have a changing state of matter, it's a physical change. Don't get tripped up, okay? Especially with you honors kids. Chemical changes. A new substance is formed. So I'll let you look at these examples and write them down in the box. But some of the key examples would be rusting metal, okay? That metal that's rusted has actually been eaten away. It's oxidized. It's become iron oxide, for example, a bike chain. Rotting fruit. Anytime you have something that's rotting, sour milk, burning, okay? Explosions, photosynthesis, digestion. Anytime you eat something, okay, and it's going through your stomach, it's going through a chemical reaction. If you eat a slice of pizza, that pizza will no longer be a pizza in 24 hours, okay? It's going to go through a change and it's going to become a new substance, okay? So these are some examples of chemical changes. Okay, so the next topic that we covered in this class was states of matter. So you guys remember the 3 states of matter since you've been a little kid, right? Solids, liquids, and gases. What we've learned is that all matter is made of particles. Many times we don't think about this. When we see a table, we just see one table. But we're actually looking at a substance that's composed of billions and trillions of particles, known as atoms. And so what we've learned is that there's 3 states of matter generally that we talk about: solid, liquids, and gases. And as you can see on this video right here, that the particle structure of each state of matter is different. So what I'd like you to do in your booklet is, for each state of matter, draw how the particles are in each box. So you can go ahead and pause the video and work in your booklet with this part of the booklet, okay? Obviously, you can see right away that there's big differences between the particles in each state of matter. Solids are more organized, okay? They're closer together. Liquids are looser and gases are free particles. One of the things that you have to be able to do is you have to classify matter. You have to classify solids, liquids, and gases in terms of different characteristics. And these characteristics are shape, volume, and compressibility. And I also want to add order structure, okay? So what I'd like for you to do is, on your booklet, it asks you to describe the features for each state of matter, such as order structure, shape, and compressibility. So let's talk about this. Solids are very ordered. You cannot change the shape or volume of a solid. They're both fixed. And you cannot compress a solid. It's not compressible. No compressibility. What is the definition of compressibility? It is the ability to decrease the volume of matter by increasing the pressure. So, in other words, can you pack something in and make it smaller by adding pressure to it? In solids, you really cannot. Liquids, they're less ordered. They have a fixed volume, but they can actually change shape. So if you have a liquid, it changes shape based upon the container it's in. I think you guys have known this your whole life, okay? Liquids are not compressible. Gases have a random order. Their particles are free. Think of them as like little kids in a bouncy house just going all over. Gases do not have a fixed volume of shape. They literally can change according to whatever container they're in. And you can compress a gas because remember, those gas particles are free and they're all over the place. So if you add pressure, you're slowly putting them into a smaller amount of volume, okay? So that's a quick review on solids, liquids, and gases. Next, we're going to move on to pure substances and mixtures, okay? This is another way that we classify matter. And each type of matter, a pure substance or a mixture, has certain properties. And you need to be able to classify matter based on if it's a pure substance or a mixture. So how do you know if a substance, how do you know if matter is, let's say you're walking down the street, you run into some matter. How do you know if it's a pure substance or mixture? So what is a pure substance? Okay? A pure substance is either an element or a compound. And I think by now in this class, if you've been following along the class, you know what an element is. An element is a substance that's only made up of one type of atom. So gold is an element. It's only made up of gold atoms. A compound is two or more different types of atoms bound together. Okay? And the thing about compounds is we've talked about like ionic and covalent bonds, right? And those electrons are actually bound. They're either shared or they're bound like magnets together. So you can't, the key thing about pure substances is number one, again, it's either going to be an element or a compound, and they cannot be separated. You cannot separate a pure substance. It's pure, okay? Let's move on to a mixture. A mixture is a blend of two or more kinds of matter. It can be separated. So one of the major differences already is if you see a piece of matter and you cannot separate it physically, it is a pure substance. If you can separate it, it is a mixture, okay? You have two types of mixtures. You have homogeneous mixtures. These are mixtures that are mixed evenly. They're evenly spread out, okay? And there's some examples on the screen. So you have homogeneous mixtures, they're evenly mixed, and then you have heterogeneous mixtures. They're mixed unevenly, okay? So you need to know the difference between the two types of mixtures. Now, something you may see on your test is a look of how the different particles of pure substances and mixtures look like. So you have an element. Here you have four types of matter, right? You have an element, you have a compound, you have homogeneous mixture, and you have a heterogeneous mixture. These are how the different substances look like. If you look at an element right here, I'm highlighting it with an arrow. See how it's only made up of one type of atom, okay? So all of these atoms right here, look at that. They're all blue atoms, okay? Let's say that that's gold, okay? So pretend that all you see is one type of atom, and that has to be an element, okay? Let's look over here. If you look at a compound, right? So you see it's actually only one type of matter because these are all the same, right? But look, it's a compound because, and let me erase this real quick. Because look, you have two different types of atoms. That's one, number two, the gray, and then the gray is the first type of atom, and then the red is the second type of atom. But they're bound together chemically. You cannot separate them physically. That's why they're a compound, okay? Now let's look at the mixtures, okay? Here you have an homogeneous mixture. What is a homogeneous mixture, guys? Remember, evenly mixed, evenly spread out, okay? Then we have heterogeneous, unevenly mixed, okay? So think about Kool-Aid. Think about tea. You want your drinks to be homogeneous mixtures, right? So that the flavor is evenly spread out. You don't want to drink something and then it tastes like water, and then at the very end, it's like really super soury or something like that, right? So make sure that you understand what these particles look like, and then go ahead and draw them in your booklet, because I believe that it asks you to do that, okay? Next, we're going to talk about modern atomic theory. How did we get to this point in humanity where we understand about the atom. Who gave us this knowledge? We talked about this in the beginning of the year. And this is what this unit is about. So in your booklet, it wants you, we talked about 4 major contributors. And so in your booklet, it's asking you to write or draw the missing information for each contributor to our modern atomic theory. So it's asking you for the scientist's name, the name of their model, designing the model, and major conclusions of each model. So let's start with John Dalton. And unfortunately, I didn't put his first name, so I'm going to put that here. John Dalton, okay? The name of his model was the bowling ball atomic model. Okay, I think you guys remember that. And it's pretty easy to design the model because it just looks like a bowling ball, okay? Or one of those billiard balls. It's also known as the billiard ball model, okay? Billiard ball is just a pool ball where you go play pool with your friends, okay? So designing it is really easy. And what were the major conclusions of John Dalton's model? He believed that atoms were tiny individual spheres that cannot be divided. So the bowling ball was it. You can't break it up. You can't split it. There's nothing smaller that's underneath. The atom is the smallest particle in the universe. So that's where we stood in the year 1803. Moving on. About 100 years later, well, maybe 97 years later, J.J. Thomson came onto the scene, and he gave us the plum pudding model. I think you guys remember that you guys designed this, okay? The plum pudding model. And here was the design, okay? I'm going to draw an arrow to it. Remember, J.J. Thomson was a British man, okay? And so in his day and age, plum pudding was like a very common dessert at the time. In America, you can kind of think of it as kind of like a blueberry muffin. So to J.J. Thomson, this was his design, okay, that I'm drawing arrows to, okay? And so what you had was you had kind of like a cake where the cake part was the positive charge, okay? And then the little chips were the electrons, okay? So if you think of it in terms of the United States, and we think of like a blueberry muffin model, think of these electrons as the little blueberries, okay? So I'm going to do electrons, blueberries, okay? And they were negatively charged. And then this little yellow part was the cake part, and it was all positive, okay? So that was J.J. Thomson's plum pudding model. The major conclusions of his model was that all atoms have electrons. And he actually discovered the electron in a famous experiment that we're going to talk about a little bit later. And because he discovered the electron, he concluded that unlike what John Dalton thought, atoms could be divided into smaller particles because he discovered one, okay? And he also concluded that an electron is very small compared to its charge, okay? So that was J.J. Thomson. Moving on to Ernest Rutherford. He gave us the nuclear model in 1911. And this is how the nuclear model looks like. I just circled it, okay? So, Ernest Rutherford concluded that atoms have a tiny and heavy center called a nucleus. This nucleus must be positively charged. He also concluded that the nucleus is small compared to the total size of an atom. So, when we think about an atom, we think about the nucleus in the center, the electrons surrounding it, orbiting it, okay? Well, the nucleus is so small that if we compared the total size of an atom to a football field, it would be like a marble in the center of a football field. That is how small the nucleus is. And these were the conclusions that Ernest Rutherford drew in 1911. And he also concluded that electrons orbit around this nucleus. So this was Ernest Rutherford's contribution to the atomic model. Next, we had Niels Bohr in 1913. He gave us what we basically call the Bohr atomic model. We named it after him, okay? And this was the design of the model, okay? I'm going to go ahead and just draw a little arrow, and this is the Bohr atomic model. Its major features are that you have a nucleus in the center, and you see how you have these energy levels that the electrons orbit. It's kind of like rings around the nucleus, okay? So electrons orbit the nucleus in specific energy levels, kind of like planets revolving around the sun. So we sometimes think of the Bohr atomic model as a planetary model, okay? And I'm going to go ahead and write planetary model. So if you were to see something like this on the test, where you have a nucleus like that in the center, then you have different energy circles, and you have electrons floating around, you know that this is the Bohr atomic model, okay? Because it looks like planets revolving around the sun in our solar system, okay? Modern atomic theory, the two famous experiments that were instrumental in giving us our current knowledge of the atom. Ernest Rutherford, the gold foil experiment. So on the right hand side, I'm going to circle it. This was the design of the gold foil experiment. So please pause the video and draw this on your booklet. And remember to label everything, okay? So, who conducted this experiment? Ernest Rutherford. What was discovered? Let's talk about this and what were the major conclusions. Ernest Rutherford shot alpha rays at gold foil. Most of the rays passed, but some deflected back. Ernest Rutherford discovered the nucleus. So this is huge. You need to understand that Rutherford discovered the nucleus via this experiment, okay? So if there's anything that you remember, try to remember this image, that it was conducted by Rutherford and he discovered the nucleus, and it was called the gold foil experiment, okay? And the conclusion that he came from this experiment is that atoms have a small and positively charged nucleus in the center, okay? So you need to know this. The second famous experiment was the cathode ray tube experiment, conducted by J.J. Thomson. J.J. Thomson shot a stream of cathode rays in a tube. He observed the rays bent. So this was the ray. You see this little blue line right here that I'm highlighting, okay? I just highlighted that blue ray, okay? So J.J. Thomson shot those in a tube. He observed that these rays bent towards the positive plate. So whatever he was shooting, if it gravitated towards the positive plate, it must be negative. So he discovered the electron. And he concluded that atoms are made of smaller particles and that electrons have a negative charge, okay? So let's go back. And by the way, design this experiment right here. You need to design this in your booklet, okay? So let's talk about this. What are the key words? You need to understand by looking at this that it was the cathode ray tube experiment. It was conducted by J.J. Thomson, and that as a result of this, he discovered the electron. Okay? Try to keep things really simple, students. Next, we're going to talk about the electromagnetic spectrum. So just take a look at this. All the energy in the universe is electromagnetic radiation. And radiation comes in different wavelengths, comes in different frequencies and energies. And just take a look at this. We have, I believe it's 7, okay? We have 1, 2, 3, 4, 5, 6, 7 types of radiation that we generally talk about in chemistry and in physics. Okay? We have radio waves, we have microwaves, infrared, visible light, ultraviolet light, X-rays, and gamma rays. And if I draw an arrow, this is an arrow in order of increasing energy, okay? Radio has the lowest energy. Gamma rays have the highest energy. See this green right here? Remember, the Incredible Hulk is a big green monster, right? He became the Incredible Hulk due to gamma rays, high energy rays. So they have the highest energy. So I like to think of this as the Incredible Hulk is green due to high energy gamma rays. But whatever you need to do to remember it, because you have to remember the order, guys, that this comes in, okay? So what should you do? In your booklet wants you to draw the electromagnetic spectrum. So yes, in order of increasing energy from left to right. So this is going to be good practice, okay? But you know what? Before we do this isn't in your booklet, but I did want to talk to you about wavelength, frequency, and energy. And again, this is not in your booklet, but this is a great review because you need to be able to understand the relationship between these three things, okay? So what is wavelength, okay? Here's a wave, okay? What is wavelength? Wavelength is the distance between two identical points on adjacent waves, okay? So let's just take this point right here that I put a star, and then I'm going to find its exact same spot on the next wave. And that's it right there. So wavelength is the distance between these things. You see that? That's a wavelength, okay? So let's say that this wavelength is 5 meters long, okay? What is frequency? Frequency is how many waves pass in a second, okay? So if 2 wavelengths pass in a second, okay, that is its frequency. You have 1 wavelength per second, okay? So what's the relationship between wavelength and frequency? As wavelength decreases, frequency increases. So they're indirect. So if wavelength gets shorter, so the more scrunched in a wave is, the higher frequency it has. The longer a wavelength is, the lower its frequency, okay? So let me go over that one more time, okay? Because some people can get a little confused, okay? Let's look at a wave. Okay, let's have 2 different waves, okay? Which wave has which is the shorter wavelength, okay? Obviously, the one on the bottom is shorter, okay? This is the shorter wavelength, and the one on top is the longer wavelength. So what does this mean? The top one has lower frequency, okay? The bottom shorter wave, because the wavelength is shorter, it has higher frequency. So one of the ways that I like to think of it as, the more scrunched in. So pretend you have an accordion. So the accordion is scrunched in like this that I'm drawing. It has high frequency, okay? And I like to think of it as a more scrunched in wave. Think of it as like boom, like a laser that's like super focused, okay? Really scrunched in with a lot of power behind it. That's high frequency. That brings me up to my next relationship, okay? What is the relationship between frequency and energy? So here we have a short wavelength, okay? And here we have a longer wavelength. So the top one has a shorter wavelength. So it has high frequency, okay? Therefore, it has high energy, okay? The more the frequency increases, the more energy increases. So they're directly related. As frequency increases, energy increases, okay? So the bottom one, it's a longer wavelength, okay? So as wavelength increases, we have higher wavelength and we have lower frequency. So we have lower energy. Just remember that energy and frequency go hand in hand, okay? But I wanted to cover that, okay? Because I know it's been a long time since we've studied this, okay? So now, I apologize for that, but that was very important for you to understand. So now, go ahead and draw the electromagnetic spectrum in your booklet. So yes, I want you to draw a little picture of a radio, and yes, a microwave that you use all the time. Infrared that police use or to hunt criminals at night, or snakes use to hunt rats in the night because they can detect body heat. Write all these down, okay? And I'm going to go ahead and one more time go over this. From the left, we have the lowest energy, okay? So radio's number 1, microwave's number 2, infrared is number 3, visible light is 4, ultraviolet radiation is 6, X-ray is 7, X-ray is 6, and gamma ray is 7. Now what I want you to do is pay attention because I do want you to draw. Look at this wavelength at the bottom. I'm copying it with my Apple Pencil, okay? As you go from radio towards gamma ray, the wavelength is decreasing, guys. It's getting more scrunched in. So as wavelength gets shorter, frequency is increasing. So let me put an F for frequency, and F is getting higher. As frequency increases, energy increases. That's why gamma rays have the highest energy, guys, because their frequency is higher, okay? And their wavelengths are the shortest. Radio waves have the lowest energy, okay? And take a look at the wavelength of radio waves. They're longer, okay? Because their wavelengths are really long, their frequency is low, and their energy is low as well, okay? So keep that in mind, guys. Let's say you're taking the test and it's asking you to put radiation in order, or which one has the greatest or least energy. Okay, I know that sometimes it could be hard to memorize these 7 in order: radio, microwave, infrared, visible light, ultraviolet, X-ray, and gamma ray. One phrase that you can use to remember the order from lowest to highest energy is rich men in Vegas use expensive girls, okay? R stands for radio. M, microwave. I, infrared. V, visible light. U, ultraviolet. X, X-ray, girls, gamma ray. So once again, rich men in Vegas use expensive girls. Radio, microwave, infrared, visible light, ultraviolet, X-ray, and gamma. So hopefully that'll help you. Visible light can also be broken up into the colors of a rainbow. If you use a prism, you can actually separate visible light radiation, okay? And these are the colors that, we've known our whole lives. And what we've discovered is we have red, okay? Red is has the longest wavelength of the colors of the rainbow. Violet has the shortest, okay? So in between, let's start with red. We have red, orange, yellow, green, blue, okay? Blue, indigo, and violet, okay? There's a name that we use because, once again, this is kind of hard to memorize the colors of the rainbow in order of shortest or, longest to shortest wavelength. The name that we use, and I'm going to circle it on the screen, is Roy G. Biv. Okay, this is a man that lived, okay? So Roy G. Biv, his name helps us to remember the colors of visible light in order from longest. So I'm going to put red as the longest wavelength, and then violet is the shortest wavelength. So just based upon your understanding of the relationship between wavelength and frequency and energy, let me ask you a quick question. Which color has the highest energy? The answer is violet, because it has the shortest wavelength. So it has the shortest wavelength, it has the highest frequency, okay? But anyways, let me erase all that. Roy G. Biv, okay? So just remember the name Roy G. Biv. R stands for red, okay? O stands for orange. Y is yellow. G is green. B is blue. I is indigo. And V is violet. Roy G. Biv. I'm going to write that. Roy G. Biv. Colors of the rainbow, okay? Electron configuration. You can do this, guys. What are the keys to understanding electron configuration? The first thing you want to do is to locate the element on the periodic table. Remember, use the periodic table during this test. The periodic table is your friend, okay? It's there to help you. That's why they let you use the periodic table. So, whenever you're finding the electron configuration of an element located on the periodic table, find its atomic number. The atomic number tells you how many total electrons an element has. The second key, the total numbers of subscripts add up to the atomic number of an element. So let's take oxygen, for example, okay? What is the electron configuration of, and I didn't even spell oxygen right. Oxygens is, we locate it on the periodic table. And oxygen, and let me write this again. I can't stand that I misspelled oxygen, okay? And I misspelled it again, okay? Oxygen, there we go. Oxygen is atomic number 8. So it has 8 total electrons, okay? Now, its electron configuration is 1s2, 2s2, 2p2, okay? But what did I mean that the total number of subscript numbers add up to the atomic number? Look at these little numbers that I wrote. 1s2, 2s2, and it's actually 2p4, okay? So these numbers have to add up to 8, and they do. And see, I corrected myself because I thought it was 1s2, 2s2, 2p2, but it's actually 1s2, 2s2, 2p4. That's a good way to check your work, is if you think you have the right electron configuration, you add up those little numbers and they add up to the atomic number. Remember, when you're doing these, the correct answer must have the correct order of increasing energy orbitals. You may get an answer that the numbers add up, these little superscript numbers add up, but it'll start with 2s2 first and then 1s2. 1s2 always starts first, and then you have to know the remaining ones, okay? What I'd like for you to do is, on your booklet, you have a mini periodic table. I'd like for you to label don't worry about the F block, okay? We're only worrying with the S, P, and D block. So on your mini periodic table, label the table into the different S, P, and D blocks. So here's what I do. Circle this and put S. Circle this and put P. Then circle this and put D. Okay, if you want to label the individual ones like 2P, 3P, go ahead and do this. But the main thing is that you understand where the S blocks are at. Remember, the S blocks are these high columns of two groups, okay? The transition metals, you got 3 through 12. You got the D's are a wide grasp, okay? P's, okay? You have 6 wide, okay? The main thing is you understand where S's are at, P's are at, and D's are at, okay? All right, so starting from, let me erase that. Starting from 1s, write the increasing energy orbitals until 4d. So this is good practice, okay? So you always start it, and I'm just going to go with I'm just going to circle them with my pen as I go. First energy level, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10. Question: what is the electron configuration of silicon? What would you do? How would you solve this? The first thing that you always want to do is you want to go to the periodic table. You're going to locate sulfur on the periodic table. It's atomic number 16, so you know that it has 16 electrons. But that's just the first reason why you're going to the periodic table. The second is you're going to the periodic table to understand what block does it reside in. Silicon resides in the what block, guys? Pause this video and then I'll give you the answer. Silicon is in the P block, okay? And it's actually the third row down, so it's in the 3p block, okay? So what you want to do is you want to write all the increasing energy orbitals until you get to 3p and fill them up. 1s2, 2s2, 2p6, 3s2. Okay, so now we're in the 3p's. So we have to be careful. Sulfur is the fourth element in the 3p block, so it is 3p4, okay? That is the electron configuration of silicon. Now let's add up all the subscript numbers and see if it tallies up to 16. Okay. Actually, I just did the electron configuration of sulfur, so I made a mistake, okay? You see how you have to be very careful when you do these things, okay? So silicon is atomic number 14, okay? It's in the P block. It's in the 3p block, okay? So let's start over. 1s2, 2s2, 2p6, 3s2, 3p, and then silicon is 3p2 because it's the second one, okay? Now let's add up all the numbers. 2 plus 2 is 4. 4 plus 6 is 10. 10 plus 2 is 12. 12 plus 2 is 14. This is the correct electron configuration of silicon, and it's in the correct order of increasing energy levels. Next question. What is the electron configuration of potassium? First thing you want to do is you locate potassium on the periodic table. It's number 19. It has 19 electrons. It's in the S block, and it's in the fourth row down, fourth energy level. So its configuration is going to end in 4s something, okay? That looks like a 4-5, and I don't want that to look like that. So I'm going to say I want it to end in the 4s block, okay? So what we're going to do is we're going to write all the increasing energy orbitals until we reach 4s, okay? 1s2, 2s2, 2p6, 3s2, 3p6. Okay, so now we're at the 4s block, and because potassium is the first element in that block, it's 4s1. Let's add up all the numbers and see if we get to 19, okay? 2 plus 2 is 4. 4 plus 6 is 10. 10 plus 2 is 12. 12 plus 6 is 18. 18 plus 1 is 19. It's the correct electron configuration. Now, a note at the bottom. Remember, do not memorize the increasing energy orbitals. I mean, it's great if you do, but don't kill yourself. Use the periodic table. Use your knowledge of the position of the S, P, and D blocks to write electron configuration. Go row by row until you reach the element. And remember, just like I did my checks, okay? The total number of superscripts must add up to the atomic number of the element. So as you're doing electron configuration, you must use your periodic table during these questions. If you're doing these questions on the ACP and you're not using your periodic table, something is off, okay? You're probably going to get it wrong, okay? Just giving you a heads up. The next thing is, the next topic that we learned about was periodic table families, okay? And in your booklet, it wants you to label the 5 families we have studied, including the number of valence electrons each family has. So we covered 5. So forget the boron family. Do not do the one that I'm writing out. Do not do the carbon family. Do not do the nitrogen family. Do not do the oxygen family. So on your blank mini periodic table in your booklet, take the first group and you're going to label it as the alkali metals, okay? The second family is the alkaline earth metals, okay? And these have 2 valence electrons each. The alkali metals have 1. The third group, it's that lower valley of the periodic table. These are the transition metals, okay? So this is group 1, alkali metals. Group 2, the alkaline earth metals. Transition metals are groups 3 through 12. Now we have the halogens, okay? The halogens are in group 17 and they have 7 valence electrons each. Finally, at the very end, we have the noble gases and they have 8 valence electrons, okay? So make sure you label your periodic table. These were already labeled, lucky for you, but you need to know where these are at because you get a question on the test where it says, and there's no labels, pretend that there's no words that you're looking at. It says, what is this family over here that I just marked with an asterisk? It's the alkaline earth metals, but would you know that if you went into a test? Because you're not going to get a periodic table that has the families labeled. Okay, so the next thing you need to do is you need to understand the characteristics of each family. And that's what it wants you to do in your booklet. Alkali metals, group 1, they have 1 valence electron. They're the most reactive elements on the periodic table. They lose 1 electron to have a full valence shell. Alkaline earth metals are in group 2. They have 2 valence electrons. They're reactive, but less reactive than group 1. They lose 2 electrons to have a full outer shell. The transition metals are groups 3 through 12. They're good conductors of heat and electricity, and they're solids at room temperature. The next group is the halogens. They're group 17. They have 7 valence electrons. Halogens is a Greek word that means the salt makers. Why do we call them the halogens? Because they react with metals on the left side of the periodic table to form salts. One of the greatest examples of this is the salt that we use to eat every day. It's made from chlorine, okay? Chlorine is a halogen, right? In group 17, it has 7 valence electrons. Salt or sodium, pardon, I'm getting ahead of myself. Chlorine, which is an halogen, will react with sodium on the left-hand side of the periodic table and form the salt. So from a gas, chlorine, and from a metal, sodium, we get a salt. Okay? That's an example, a famous example of a halogen, chlorine. Halogens tend to gain 1 electron to have a full shell. All of them are gases except astatine, okay? Finally, we have the noble gases, and it's very important for you to understand what makes the noble gases so special. They're group 18 elements. They're the furthest group on the right-hand side. The noble gases have a full valence shell of 8 electrons. Remember, the octet rule states that atoms want 8 valence electrons in their outer shell to be happy. Well, the noble gases naturally have this. Because of this, they're extremely stable and they do not react with anything. And obviously by their name, all the noble gases are gases, okay? So make sure that you remember the traits of these family members, okay? The next thing that we learned in class was periodic table trends, okay? So you need to understand in your booklet, it wants you to write the definition for each property. And then with arrows, like you see on this screen right here in the video, It wants you to show with arrows how each property increases on the periodic table. So what is atomic radii? Atomic radii is the size of an atom. And it increases from top to bottom. So I'm going to go ahead and take my pen and draw an arrow. It increases from top to bottom, from right to left, and then it increases from fluorine all the way to francium, okay? So that's atomic radii, the size of an atom. You may be asked about in honors classes or even in regular chemistry on this exam. Why does atomic radii increase as you go down the periodic table, down a group, okay? The reason is because as you go down the periodic table, so take a look as I go down on the left-hand side of the table. See how I'm going down? I'm going to write the period numbers 1, 2, 3, 4. Look at the left-hand side of the periodic table. 1 to 7. Those are the period numbers, okay? Obviously, as you go down, it increases. So 1, 2, 3, 4, 5, 6, 7. As you go down, the number of circles around the nucleus or energy levels increases. So by the time you're at the 7th energy level on the bottom, there's literally 7 circles around that nucleus. So that's why the size of an atom gets bigger as you go down, okay? One question that you may not get, but I want you to be prepared for it. Why does atomic radii decrease as you go to the right? Okay? As you go to the right, the atomic number increases. So the number of protons is increasing as you go right. So if the number of protons increases, that means that the nucleus in the center is getting more positive and more positive. So those electrons on the outside are more attracted to that nucleus. So the size of an atom or atomic radii gets smaller as you go to the right because that positive, bigger nucleus is pulling those electrons closer and closer, and it's scrunching in the size of the atom or its atomic radii is getting smaller, okay? So make sure you write how this trends with arrows, okay? Next, we have ionization energy. The definition of this is the energy required to remove an electron from an atom. It increases from bottom to top, from left to right, and from francium all the way to fluorine, okay? So on your booklet, make sure you're using these arrows. First of all, write the definition for ionization energy and then use arrows to show how it trends on the periodic table, how it increases, okay? Electronegativity is defined as how well an atom can attract electrons from other atoms. It trends the exact same way as ionization energy. And let me go ahead and delete that from the middle. Should have been electronegativity. So it increases from bottom to top, from left to right, and from francium to fluorine, okay? So make sure you write that in your booklet. And like I said, there's more properties of the periodic table, but we stick to 3. So it could be more difficult, guys. So we have atomic radii. Just remember radii. Okay, the size of an atom, ionization energy, and electronegativity. And here I'm writing like a doctor, okay? Average atomic mass. Take a look at this, okay? These are the different isotopes of carbon. Carbon-12, carbon-13. This here is an example of what we're talking about. If you could understand this, and if you could understand this, then you're good to go with average atomic mass. But let's go over this, okay? First, what is atomic mass? Atomic mass is the number of protons and neutrons combined. On the right-hand side, this is an example of nuclear notation. It could be an example of something that you see on the test. So here we have aluminum-27. 27 is the atomic mass. So what does that mean? 27 means the number of protons plus neutrons combined. So how can we figure out how many neutrons we have from atomic mass? The answer is you subtract it from its atomic number. If we know, based on this nuclear notation, if we know based on the atomic mass that 27 is the number of protons and neutrons, and we know the atomic number based on the element, then we can subtract the atomic number from the atomic mass and get the number of neutrons. So on this screen, in this particular isotope of aluminum, 27 minus 13, we have 14 neutrons in this atom, okay? So that's how you determine the number of neutrons based on atomic mass. You subtract the atomic mass from the atomic number. What is an isotope? Huge question. An isotope is an element with a different number of neutrons. So let me flash back to this example on the title screen for this topic, okay? So we have carbon-12. Carbon-12 has 6 neutrons. Carbon-13 has 7 neutrons, okay? That's what an isotope is. What is percent abundance or natural abundance? How often we find an element on Earth relative to its other isotopes. And they typically give this to us in a percentage. Like the percent abundance of copper-12 is 80%, okay? And you always have to convert that to a decimal when you're calculating, okay? So 80% would become 0.80, okay? What is the formula for average atomic mass? Your booklet is asking you to do this, okay? So it's asking you to write the formula for average atomic mass and then to also state what M and P stands for, okay? One note, this formula that I'm circling right now, this formula is for 3 isotopes. If you were given 3 isotopes in the question, you would use these 3 different groups of parentheses, okay? You use as many groups of parentheses as you need based on how many isotopes you have. If all you have are 2 isotopes, guess what? You're only going to use what I just circled, the first 2 groups of parentheses. If you have 3 isotopes, then you're going to use the formula that I wrote down here, okay? Pause this video, write this formula down that I just circled. Also, write down what all the M's and P means, okay? So please pause that video. Pause this video. The next thing you have to do is you have to remember to convert percent to decimal, okay? So 75%, if you see that as a percent abundance, you have to convert it to 0.75. If you don't do that, it could cause problems for you, just letting you know. Okay, let's move on. Ionic and covalent dot formulas. Ionic bonds, okay? What are ionic bonds? Ionic bonds are valence electrons that are lost or gained between a metal and a non-metal. Very important for you to understand that. What do ionic bond structures show? Ionic bond structures show the new charge atoms have after losing or gaining electrons. Losing electrons makes you more positive, and gaining electrons makes you more negative. Include the non-metal in brackets and give it a full shell of valence electrons around. So this is a very classical example of an ionic bond. We have sodium. Sodium is the metal. We have chlorine, okay? Chlorine is the non-metal. So metals will lose their electrons and the non-metal will gain the electrons. So ionic bond structures are all about the charges after they lose or gain electrons. So sodium has 1 valence electron. So when you're doing these bonds, you have to understand the valence electrons, okay, of the metal that's going to lose it, okay? Sodium has 1 valence electron. It's going to lose that electron, and therefore it's going to become a positive ion, okay? Chlorine's going to gain the electron, so it's going to be a negative ion. And We only put positive and negative, and we don't add any number to that because each one gained or lost one. So we don't have to add that one. It's understood. But if it was any other ionic bond, we would change it. Okay? So for example, on the left-hand side, let's do magnesium oxide, okay? Magnesium has 2 valence electrons. So magnesium is going to lose those valence electrons, and it's going to become a positive 2 ion. So you might say, well, oxygen has 6 valence electrons. But you don't write that. Oxygen is going to gain those electrons, so it's going to be 2 negative. And then you give it a full valence shell of 8 as a result of gaining those 2 electrons, okay? Because it had 6 earlier. So that's ionic bond structures. Covalent bond structures. What are covalent bonds? Covalent bonds are valence electrons that are shared between 2 nonmetals. So there's already 2 differences between ionic and covalent bonding. In ionic bonding, electrons are transferred, that they're lost or gained. In covalent bonds, they're shared. Ionic bonds deal with a metal and a nonmetal. Covalents deal with 2 nonmetals. The key to understanding covalent bonds is you need to remember that every atom in the structure that you draw needs 8 valence electrons around it, except for hydrogen that only wants 2. And also the key is to remember that shared electrons are represented by a line, and a line is worth 2 electrons. Here are the rules to writing covalent bond structures. The first thing you want to do is you want to count the total number of valence electrons, okay, in the bond. 2, you want to put the single lone atom or carbon in the center. What do I mean by the single lone atom? The single lone atom is the element in the bond that there's only one atom of. So if you have carbon dioxide, CO2, there's only one carbon, so it goes in the center. If you have CCl4, okay, it goes in the center. Anyways, carbon always goes in the center, and the lone atom always goes in the center. So if you had SF2, there's only one sulfur, so that would go in the center. 3, distribute valence electrons to outer atoms until each has an octet, or 2 for hydrogen. 4, add leftover electrons to the central atom. 5, use double or triple bonds if the center atom doesn't have 8 full valence electrons around it. And 6, do a check to make sure all atoms have a full shell. So here's the covalent bond structure for sulfur dioxide, SO2. So on your booklet, I want you to draw this, okay? And by drawing it, I want you to understand a couple of things. I want you to be able to look at this and study it. The first thing I want you to understand is how each atom has 8 valence electrons around it. So let's look at the oxygen on the left. Okay, this oxygen has 2, 4, 6, 8 valence electrons around it, so it's happy. Remember that a line is worth 2 electrons, okay? So we just did a quick scan of this oxygen, and we discovered that it's actually satisfied, okay? Next, let's take a look at this sulfur atom. It has 2, 4, 6, 8, so this sulfur is satisfied, okay? Now let's take a look at the oxygen on the right-hand side. Oxygen has 2, 4, 6, 8 valence electrons. It's also satisfied. But remember, check your work. Does the total number of electrons in this structure equal the total number of valence electrons, okay? So sulfur dioxide, we have 1 sulfur atom. Sulfur has 6 valence electrons. We have 2 oxygen atoms. Each oxygen has 6 valence electrons. So the total number of valence electrons is equal to 18, okay? Keep that in mind. So where am I going with this? Do a check on your work, okay? Let's count all the valence electrons in this structure. 2, 4, 6, 8, 10, 12, 14, 16, 18. The number of valence electrons in this structure is 18. We know that there's 18 total when we did the count on this bond. And we also did a count to make sure every atom in this structure has 8 valence electrons around it. So a test-taking strategy that you want to do is, if this is a multiple choice question, you may be panicking and tell yourself, I don't know how to do this. Well, you may not even have to. What do I mean by that? Take a look at all the multiple choice answers and do a process of elimination. If you're looking at a test and multiple choice answers for the correct covalent bond structure, first of all, add up all the valence electrons and make sure that the structure, they add up to those total number of valence electrons. The next thing you could do is do a scan to make sure every atom is happy. You can do a scan on all 3, and if one of them isn't happy, you know that that's not the correct answer. So I believe that based on those 2 tips, you could actually get away with not even having to know how to do the structures, simply because it's a multiple choice exam. Now, it may be drag and drop, and they may be moving towards more of a write in the answer. So be very careful with that. You never want to just depend on that. Okay? Next, we're going to move to the mole in Avogadro's number. This is it, guys. Okay, I know that you're tired, and I know it's been a long semester, and we're not even through yet, guys, but you just have to power through, okay? So the mole in Avogadro's number. What is the quantity of a mole? 1 mole in chemistry is equal to 6.02 times 10 to the 23 atoms, okay? I know that you've heard that number a lot, probably. Pardon my voice. Once again, 1 mole is equal to 6.02 times 10 to the 23 atoms. That number has a name. 6.02 times 10 to the 23. The name of that is called Avogadro's number, okay? And here's something helpful about Avogadro's number. For the ACP that you take, you will actually be given Avogadro's number on the test. They will give that number to you. So if you forget the number, it's included as one of the constants on the exam. So I never want you to get to that point. I want you to memorize the number so that when you go into the exam, you don't even need to use it, but it's helpful just in case you forget, okay? Keep that in mind. What is molar mass? Molar mass is the weight in grams of 1 mole of an element. Molar mass is found on the periodic table. So 1 mole of oxygen, let's look at oxygen right here, right? 1 mole of oxygen. In 1 mole of oxygen, there is 6.02 times 10 to the 23 atoms of oxygen. And 6.02 times 10 to the 23 atoms of oxygen weighs 15.999 grams. This is the molar mass of oxygen, okay? So that's the relationship between moles, molar mass, between moles and molar mass, okay, and quantity of atoms, okay? You need to be able on your booklet. Oh, and by the way, you find molar mass on the periodic table. I think I told you that, but just a second reminder. So you're going to need your periodic table, and you need to understand how to find molar mass, okay? Let's move on. After I erase this stuff. In your booklet, it wants you to write a conversion guide from moles to atoms, okay? So I want you to draw this, okay? I want you to write this. So go ahead and pause the video and write what you see on the screen, okay? The first one is the conversion guide. This is a conversion guide, and then this is an example, okay, of using it, okay? So pause the video and then write this in your booklet. Only write the conversion guide. You don't have to write the example, okay? I just gave the example for you to see an example problem and how you would use this conversion guide to solve the problem. So please pause the video and write the conversion guide. Okay, let's go ahead and move. So moles to atoms is the easiest. What you essentially do is you just multiply the number of moles times Avogadro's number, and there's your answer. But you may get a question that says, how many atoms are in 5 grams of gold, okay? So you can't convert from grams to atoms in one step. You have to go from grams to moles and then from moles to atoms, okay? So like the first one, your booklet wants you to write the conversion guide. So the top one is the conversion guide, so please go ahead and write this down, okay? I'm circling it. The one on the bottom is just an example, so you don't have to write this, okay? So pause this video and then write the conversion guide. Okay. That is it, guys. That's the review up until now. What I want to say is, have a happy Thanksgiving, guys. You guys should be commended for your hard work. I'm going to try to draw a turkey as best as I can. I'm not a very good artist. There's my turkey. There is a turkey leg. Yum, okay? Have a happy Thanksgiving. Please work on this packet. Please prepare. This is a